In this video, we are going to talk about op amps because they are very often used for different kind of applications, and we are going to talk to Arthur about this. So my very first question would be like, why op amps are so important, and can you tell some kind of examples where we would like to use them?
Sure. Basically, any analog signal, such as audio or maybe pressure, or later we're going to see a pH demo, any kind of thing that you're measuring, usually that signal cannot be directly connected to an analog to digital converter. Ultimately, you want to take analog signals like light and sound and so forth and convert them to a digital signal so that you could process it. But you have to have some way of boosting up that signal or amplifying it so that the analog to digital converter can accept it. So op amps are the most popular way of doing that because they're simple. Before, op amps, there was discrete transistor amplifiers, and it's a little bit more complex to put it together. And for an op amp, you can basically set the gain with 2 resistors, and of course there's more complex configurations, but they're simple to use.
Okay, so first, how does it work, and what are the basic circuits what we can use with op amps?
When you're talking about op amps, usually you want to start with the ideal amplifier, and that's what I'm showing here on this slide. The reason why you want to basically start with the ideal amplifier is because that's easy to analyze. And then what you do after you understand the operation of the ideal amplifier is you start adding in non-idealities to make it closer to reality. But the truth is, though, that most op amps are not far from the ideal. I mean, they're actually pretty close. So what is an ideal amplifier? The ideal amplifier has an input signal that's between these 2 inputs, and one input is called the inverting input, marked with a minus sign, and one input is called the non-inverting input, marked with a plus sign. And that differential signal gets multiplied by the open loop gain of the amplifier, which is extremely high. In fact, when you talk about an ideal amp, it's infinite. And that might seem kind of weird, but we're going to see how useful that is in a moment. But basically, if you think of the gain as being infinite, and you have some finite output signal, let's say it's 5 volts, but you divide that 5 volts by an extremely high gain, or basically an infinite gain, the differential input becomes 0. And so that 0 differential input, if you've done a little study on op amps before, that's what we call the virtual short. So it basically it connects these 2 inputs together because the voltage is 0 between the 2. But they call it a virtual short because there's actually no current flowing through that. Like a normal short circuit would allow a lot of current to flow. But the virtual short happens by virtue of the high gain of the amplifier. So that's the most important ideal characteristic. But then we have basically the offset voltage between these 2 pins is 0 on an ideal amplifier. And then maybe even more important, the input bias current, or the current flowing into these 2 inputs, is 0 because the input impedance of the op amp, or the impedance looking into these 2 inputs, is very, very high, or in the ideal case, infinite. And then real amplifiers have power supplies. They're kind of indicated with these pins here. And in the ideal sense, you don't really have to worry about the power supplies. There's no limit in place because of those supplies. But of course, in a real device, if the power supply is 5 volts, the output can't be greater than 5 volts.
So basically, when you say the amplification is infinite, it means 5 volts, or the power.
Uh, when I say
Like
the
the
gain,
A wall, yeah, is infinite. Yeah, gain
yes.
is infinite.
So,
It means on the output there will be the voltage what is on power supply, or
well, the output, well, if you were to leave it in this open loop configuration, which we'll see in a moment, isn't really how they're normally operated. But if you would put even some tiny little voltage on the input in this open loop configuration, then basically the output would hit one of the power supply rails. If the positive
mm-hmm,
supply is 5, it'd go to 5. If the negative, it could go to the negative supply.
mm-hmm.
So that's not how it's operated. And in the next slide, we'll see how it's operated.
But I
But
wanted to make it
um,
clear. So infinite gain, it means any little bit of voltage on input will go up to the power on the
yes,
output. Okay.
yes, exactly true. And I guess I would say, from a practical sense, the gain of an op amp is usually 1 million or higher than 1 million.
Mm-hmm.
So,
So it
and
means like if there will be like 0.000001, then it multiply by million, and that's what will be on output.
yes,
Okay.
right. That would be what we'd get on the output. Now, so here's how it's operated in a practical sense.
Mm-hmm.
So we use these feedback elements. And so in the previous slide, I said this is the open loop circuit and there's no feedback. Well, we use these feedback elements, and what they do is they allow us to get a nice controlled gain. So ultimately, the gain of this inverting amplifier is going to be the feedback resistor divided by the input resistor, and it'll actually change the sign or invert the signal. But people often say, well, how do I not just memorize the equation, but understand how to do that calculation? And it's not a difficult calculation. You just have to use the principles of the ideal amplifier. So remember that there's mainly two principles you pay attention to. One principle is the bias current or input current to the two inputs is 0. And the other principle is there's a virtual short between the two inputs. Or if one input's connected to 0 volts, the non-inverting input's connected to 0 volts, then the inverting input will also be at 0 volts. So to figure out what the output signal is, we've got this input signal right here connected to this resistor Rin. And we know that this point right here in the circuit is at 0 volts. So all input voltage is across this input resistor. So we've got 2 volts in, all 2 volts shows up across that input resistor. And you could compute then the current, because it's just Ohm's law. 2 volts divided by 1 kilo ohms gives you 2 milliamps. And that 2 milliamps flows through Rn, but it's also going to flow through Rf because there's no current IB flowing into the amplifier. So the current only has one path to flow. It flows through Rf and it flows through Rn. And then that means that the output, you can measure the output pin with respect to ground. And of course, the inverting inputs connected to ground by the virtual short. So the output is minus 4 volts. So that's how you could do the basic simple analysis for an op amp. And you could also do it algebraically.
Go back.
This
So
is,
gain is minus 2.
sure,
Yeah. Okay.
yes. And I guess not everybody knows what gain means. Gain is just the output signal divided by the input signal. So the output signal divided by the input signal is 2 volts, the output signal is 4 volts. And so it works out to be a gain of minus 2 because the actual output is inverted relative to the input,
Okay.
or
I have a couple of
the sign is
questions.
the opposite.
So
Sure.
basically, this is the way how we can control the amplification between the input and output, correct? With
Yes.
this, for
Right.
example, with these two resistors, if you use different values, then we can multiply the input by any number we want and get it on the output.
That's right. So
Uh,
it's common to get gains from 1 to 1,000. You could even get more, but usually 1,000 is about the highest that people use for op amps. They might cascade a couple circuits and get higher gains.
So for example, we have a sensor with 1 millivolt output, and we use operating or op amps to amplify this to 1 volt.
Right. So gain of 1,000 and you get 1 volt. And that's exactly what you would do.
Okay. So how do you decide on these values of these resistors, or you have it somewhere in the presentation later?
Yes, we'll get to that. That really, so in the ideal amp, which is what we're looking at now, it really wouldn't matter. You could use 2K and 1K and get a gain of 2, or you could use 2 mega ohms and 1 mega ohm and get a gain of 2K, 2 volts per volt. So it doesn't matter in the ideal sense, but when we get to the real amplifier, that's when we'll see things like the input resistance and the feedback resistance value matters.
Okay. And I believe there are more different kind of circuits what we can use for these op amps. Okay, so what is the next
So
one?
let's look at this inverting amplifier algebraically.
Okay.
So the same exact equations, happen, but instead of computing numbers, I just put the equation in here. So we've developed an input current and that flows through the feedback, and then the output voltage is the voltage across the feedback resistor. And if you put in all the numbers, and I won't step through the algebra right now, but basically you rearrange it algebraically, and you can see the gain is basically minus RF over R1 for an inverting amplifier. Now, there's only a few different circuits that actually there's many circuits for op amps, but there's a few very common ones. So this is one of the most common circuits. So really what I recommend to people who are going to be doing this kind of analog work is memorize this equation, because you'll see this circuit over and over again. You don't want to have to rederive it every time. The other common one is the non-inverting amplifier. And you could do the same kind of analysis, but in this case, this input signal, Vn, is actually being forced on the inverting node by virtue of the virtual short. So the inverting node is at 2 volts or at Vn, and then that will be across R1 and developing an input current. And then that current has only one way to flow. It can't flow into the op amp, so it has to flow through the feedback. And the output signal will be the voltage across RF, and added to that, the voltage across R1. And then stepping through the algebra, you would find that the equation is RF over R1 plus 1. So that's a little bit different than the last one. We've got this factor plus 1, and also the sign is positive because it's a non-inverting amplifier.
Nice explanation, actually. I wish they would explain this this way when I was at university.
Well, thank you. I appreciate that. Now, the last one is really just the non-inverting amplifier, but a little bit different version of it. So if we, in this amplifier, we have RF at 2K and R1 at 1K. Well, what if we made this 0 ohms and we made that infinite? Well, RF of 0 ohms over infinite, that would just come out to 0. And that's what this is. RF is 0 ohms and R1 is infinite, or there's no resistor there. And so RF over R1 plus 1 gives us 1 for the gain. So often people say, well, why do you want to use an amplifier if its gain is only 1? I mean, the input is equal to the output. The output is equal to the input. So why bother having the amplifier? Well, the reason is our sources will have some impedance. So a source could have an impedance of ohms, single ohms, kilo ohms, mega ohms, even giga ohms, as we'll see later in the demo. And so if we were to want to drive a signal to a load from the input, and we would have these two resistors just in series, we wouldn't use an amplifier, then we'd get a voltage divider effect. Basically, the input signal would be divided by 2 in this case, but if this were a mega ohm resistor, we'd hardly get any output signal. And so the point of this buffer is to eliminate the effect of this input impedance and allow you to drive a load without having that voltage divider effect.
So basically, we can, for example, measure a signal on sensor the way that the sensor even kind of doesn't feel or doesn't see that we are measuring something.
Exactly. It has because the input impedance of the op amp is so
It's
high.
so high that it means nothing is really connected there, nothing else.
So those are the common circuits. I'll just show you this one, which is a very unusual circuit, just to show you that basically the same principles can be applied to any circuit. So this is what you call current reference. We want to make a constant current source. So we have a voltage reference, and we're using an op amp to take and force the voltage of that voltage reference to be across this resistor. So just remember the input here is the same as the output. And so if the voltage from the output of the reference to ground is 10 volts, since the input and the output are at the same potential, all 10 volts have to be across this resistor. And the current flowing into the non-inverting input has to be 0 because it's an ideal amplifier. Thus, all the current just flows into the load, regardless of what that load resistance is. So, if the resistance is, a kilo ohm or 100 ohms or an ohm, that's going to maintain a constant current. And so that's basically how you could apply the principles that we talked about in a very unusual circuit.
Cool.
And then the last thing here is just to say that these 3 circuits, you should memorize these ones because you'll see these over and over again. Probably, 80% of the work I do has to do with one of these 3 configurations.
This will be on the exam.
Yeah.
If someone is at university, this will be on the exam.
Yes. Very true.
Okay, so this is the ideal amp. Yeah, okay.
So let's talk about non-idealities. So in a previous video we did, I talked about breaking the specs up. If you look at an op amp data sheet, there's a million specifications. And the first time I looked at one, I was like, holy moly, this is crazy. There's too much information here. And so if you break it into different categories, it helps you to kind of understand the data sheet. And so the first category of specifications are what we call DC specifications. Input offset voltage is 1, input offset drift over temperature, input bias current drift over temperature, and then finally the gain error is another spec. So let's look at input offset voltage.
So these are the parameters what we need to pay attention when we are selecting op amps for our application.
Yes, and it will also let you know after you've selected it what kind of error expectation you should have. So you're right. When you're selecting the amplifier, you usually have an error target. I want to keep the error less than 1% or something like that. You would look through the amplifiers to consider how will those specs impact my overall error. And I would say that some amplifiers, we care about the DC error sources. And the demo we'll have later will show that for a pH sensor. And then there's other things like audio where the DC error sources don't really matter. They're not going to be important at all. So you have to look at your situation, and is it an AC signal that you're worried about, or is it a DC signal that you're worried about impacting the error? And so in some cases, both are important, but yeah.
So does it mean like if op amp has better AC, then it may have worse DC and okay.
Yes, it does. Usually it's optimized in one direction or the other. And then there are some that are optimized in both directions. So you might have some that have good DC characteristics as well as good AC characteristics.
Okay. What does it mean, good DC characteristics?
Well, there it basically means the error sources like offset voltage or bias current, and we're going to look at both of those, are very small. So usually you care about DC specs when your input signal source is very low frequency or near DC.
Mm-hmm.
So temperature, for example, pressure, your pressure signal probably isn't moving quickly, or your temperature signal is not moving quickly. So it's kind of a DC source. And in the case of input offset voltage, basically you could model input offset voltage as a DC voltage source on the non-inverting input of your op amp. So this is inside the op amp, and there's nothing you can do about it other than select an op amp that has a better input offset voltage. And basically, this is the non-inverting configuration we looked at earlier. The input signal in this case just adds directly to the offset. So if you look at the expected ideal output, it would be the input signal times the gain, and the gain is RF divided by R1 plus 1, or 100 in this case. So 30 millivolts times 100 gives us 3 volts out. That's what we're expecting. But because we have this offset voltage, that basically just adds to our input signal, and we end up with no longer 3.01 volts. So we have an error, and you could calculate the error as a percentage if you like, and just subtract the ideal from the measured, and then you end up with about 0.3% of error. And of course, it could be much larger. The offset in this case is a millivolt or a 0.1 millivolt. Offsets can range from 5 microvolts to tens of millivolts. So this is actually a pretty good offset. It's not a bad one, but it still introduced some error. And of course, the impact of this offset is much greater in high gain circuits, where the input signal is very small.
Is this offset going to stay constant, or it will be changing with temperature or a current, or I don't know?
That's a great question. The offset changes with temperature. That's the first thing you think about happening with offset is how it drifts over temperature. And that's specified in the data sheet as a maximum in microvolts per degree C. But it also changes with power supply. And I talked a little bit about that during a different video where we looked at power supply rejection. It changes with the common mode or input signal. And it changes with even things like electromagnetic interference. So there's a lot of factors that cause the offset to shift, but temperature is probably the first one that people think about.
So you can't just simply use calculations and correct the offset in your microcontroller or something, can you? No.
You can, and people do that. That's called a calibration. So you might have multiple amplifiers, and the analog to digital converter itself will have an offset. The amplifiers will have an offset. We'll see that bias current can generate an offset, and all those errors will lump together. And your microcontroller, what you can do is you can apply a test signal of 0 volts in, and then maybe your full scale signal in, and then you would go through a calibration where you would mathematically correct for that. So that's a common thing to do, but you can't easily calibrate out like things like temperature drift or power supply impact on offset. So some of these secondary kind of things that cause offset to shift are more difficult to calibrate out.
So you could maybe calibrate it for some kind of average offset, but the temperature influence or something, it still will be okay.
Yeah, exactly. And the other downside, of course, to calibration is it's costly, because oftentimes people don't want to do calibration because to calibrate, you have to actually apply a test signal and apply a different test signal, and then you have to make measurements, and then you have to store things in an EEPROM or in your microcontroller, basically. So it takes extra effort, and it adds cost. So sometimes people will just try and pick the optimal signal chain, make sure the offset's as small as possible, and then in other cases they will optimize by using calibration.
Okay. What is the next parameter?
So,
This is still
well,
about offset. Okay.
let's actually do a demo. I think we should just do these demos as we go through the
Okay.
presentation. Here is the hardware, and we're going to use 2 op amps. I'm putting in the OPA 211 into this test circuit, which has a cascaded amplifier. Earlier, I mentioned that sometimes you have 2 amplifiers in series to get a higher gain. And this is an example where the gain is quite high. And so I just installed these DIP adapter cards with SOIC versions of the amplifiers. And I'm putting jumpers to connect the amplifiers to the test equipment. And
so you created 2 different circuits. One is with the 188 and the other one is 211?
That's correct.
Okay.
And so here we are. We're all connected up. There's no input signal in this case. The signal is really just the output that we're looking at. And you can see in the schematic here that we're grounding the input. So the input's basically 0 volts. And what we're really just looking at is the input offset voltage multiplied by a gain of 101, because it's a non-inverting amplifier. And then that gain gets multiplied by 21. And so that's what this is showing, 101 and 21. And then the output offset measured at the output pin here would be the input offset multiplied by the gain in and the gain out. And so we have about 30 microvolts of offset for the OPA, or the typical, and of this op amp here, and 125 microvolts for the maximum, and it's getting multiplied by the gain.
So these are numbers from datasheet, or these are measured numbers? Datasheet.
This is over here, these tables are just how it would be displayed in the data sheet. And so, microvolts of offset on the input doesn't sound like much, but when you look at the output signal, they can be hundreds of millivolts or even higher. And this is actually a very low offset type device. So we can simulate this. Let's go ahead and take a look at that real quick. So here's our circuit in Tina Spice with a 12-volt power supply, and the input is grounded. And I can just say analysis, DC analysis, calculate nodal voltages, and it'll give you the DC voltage at all the probes. And so we can actually look at the output of the first one, and it should display that voltage, which is about 500 microvolts. And then the output of the second amplifier is about 10 millivolts. And now this is modeling the typical offset, and it's also modeling other things like bias current and so forth. And so the calculation we looked at earlier was a little bit simplified, but basically, let's take a look at the OPA 211 DC analysis. And this is about 133 millivolts out. And if we go back to the PowerPoint, that was this case right here for this one, the OPA 211's offset. It said typically it should be 64, and this is saying 133, but the calculation we didn't account for the offset of the second stage or the bias current effects. It was kind of a simplified calculation. So it's roughly correct.
So basically we shorted the input to ground, and we still measure the offset 133 millivolts.
Right. And
Okay.
maybe one last point is, notice that this is 133 and the other one was 10. And
Big
so
difference.
if you look at, yeah, quite a big difference. If you look at the specs here for these two amplifiers, you can see that that basically we're going from 125 on the higher offset device to 25 on the lower offset device. And I would say this one on the top is optimized more for AC. It's a very, very low noise device. And this one at the bottom is optimized for DC performance. So that kind of gives you an idea. Sometimes people will conclude, oh, well, the one on the top is the good one and the one on the bottom is not so good, but it's optimized in different ways. So let's go ahead and look at the actual demo. And so I'm going to apply 12-volt power supply and minus 12 volt. And I'm going to turn on the supplies. We are going to, actually, I have an easier way. Let's see. Import configuration from computer. We want to go with the offset.
So this will switch on everything to correct values.
Yeah.
Okay.
Yes, that's a better approach. And so if we, you can see the actual DC voltage being monitored on the oscilloscope leads. But what is maybe a little bit easier to look at is that we have the mean value down here for the low offset type device, and then the mean value here for the higher offset device.
Where do you have the probes? I see where are the outputs of the amplifiers connected?
So the outputs are connected to these two BNC connections.
Okay, because I was thinking it will be on the other side where the other amplifier is.
Yeah, and those go to the measurement instrument directly. And then this is normally where the input would be, but there's inputs grounded. Yeah.
Okay.
So that's it for offset.
Wait. Okay, so we measure 1 millivolt or minus 1.5 millivolt on the better one and 36 millivolt on the other one.
Right. And so if you look at the numbers, we're expecting somewhere between on the not as good one for offset, 64 and 265. So we're actually better than 64. And sometimes people say, well, what's wrong with my circuit? But actually, that's expected. And I might have, I don't have it, but this would be a Gaussian curve for the offset. And the typical value is basically plus or minus 1 standard deviation. So 68% of the devices are going to be in the range of, for this first one, plus or minus 30.
Typical.
The most likely value you would get would be 0. That's right in the middle of the distribution. But 68% of the devices are going to range from minus 30 to plus 30. So you're going to see, a lot of numbers that'll be much better than the typical. And then, of course, in some cases, you'll see some that go all the way up to the maximum value, but the percentage of units that are in that range are going to be much smaller.
So the simulation, so what kind of values are used for simulation? Because simulation looks a little bit worse.
Yes, so the simulation includes the typical for both of these two op amps. Now the calculation, I just looked at the input offset voltage of the first amplifier, multiplied by its gain, and then I multiplied that by the gain of the second amplifier. Now I didn't include the offset of the second amplifier or the bias current effects. And in this particular example, the bias current effects are the more profound of the two. Because bias currents flowing through these feedback resistors and introducing an error source. So this technically, if I did my calculation correctly, we should be getting the same number here as I got right here. So it's not exactly the same, but it's in the ballpark.
Okay.
All right, so let's talk about bias current very quickly. We just kind of did already. The bias current is the current that flows into the inputs. In the ideal amp, we said that's 0. In a practical amp, it's going to be nanoamps to picoamps to even femtoamps. So it's quite low, but it's not 0. And that current will flow through any source impedance from your sensor or the previous stage. And it's also going to flow through your feedback resistors. And what you always want to do is you want to translate all the error sources to an input offset voltage, because then it's easy to kind of compare to the other error terms. So basically, you put all the error sources at the same location. So to develop an input offset voltage due to the bias current for Rn is quite simple. You just take this current and you multiply it by that resistance, and that's what's shown right here. But for the feedback resistors, it flows through the feedback resistors, then gets reflected to the non-inverting input. And the way that you do that is by taking the parallel equivalent circuit, so RF in parallel with R1, and that's called REQ, and that gets multiplied by the input current to give us another error source. So we have two offset error sources, and basically those offset error sources are added together, and then that's an input offset voltage. To find the output, you would just multiply it by the gain. So that is how you would do it. Now, the same circuit that we looked at earlier, you can adjust, open up, take this jumper and move it to this resistor, and so that we have this input resistance where the bias current flows through the input resistance. And that's going to make the errors worse. So let's go ahead and look at that demo. Okay, so right now we're measuring about 1.3 for the low offset device and 36 for the higher offset device. So I'm going to take and move the jumper over for to make the source resistance 5 kilo ohms, and you'll see that the offset of the device that's not optimized for DC performance jumped to almost 300 millivolts, 285 millivolts. But the other device, its offset didn't really shift that much. And the reason is that if we look at the bias currents, the one that's not optimized for DC performance has a large bias current in the hundreds of nanoamps, and the other device has 1,000 picoamps, about 1 nanoamp of bias current. So ultimately, you're going to get much higher offset with this first one because that bias current flows through that 5 kilo ohm resistor and develops a large voltage.
So in the previous slide, also the 211 was on the top in the table. Go on page 13. Okay.
Yes. So this has the larger offset, and it also has the larger bias current by quite a large margin, 100 times greater or more bias current. And so so this part at the top, the OPA 211, is optimized for low noise and good AC, low distortion, and so forth. And it's actually, its DC performance is really quite good. It's exceptional. But this one at the bottom is what is called a zero drift amplifier, and it actually has an internal calibration circuit that calibrates off the offset. So it has an extremely low offset, these zero drift type devices.
Huh. Okay. I just keep learning.
Yes. And that's really the only DC error sources that I have, for today. Gain error is another one, but with op amps, gain error is mainly due to the resistor tolerance,
Mm-hmm.
because the op amp gain is quite high. So I think we should move on to AC specifications.
Okay.
And AC specifications relate to higher frequency signals, audio, or maybe vibration analysis, or something where the AC content of the signal is important. You don't want to distort it, you don't want to have a large noise, and you don't want to attenuate it. So maybe the most important thing with AC is the bandwidth. In other words, how much frequency content can we pass? The slew rate is how fast the output can move. And then finally, we talk about the large signal bandwidth. So let's go ahead and look at that. So bandwidth, that's the first one. And bandwidth is basically, there's a spec called the gain bandwidth product, and that tells you how much bandwidth the op amp has in a gain of 1,
Mm-hmm.
really. And so if we want to calculate the actual bandwidth in different gains, we first have to calculate the signal gain. So RF over R1, or actually the noise gain is really what we want. So the bandwidth is always calculated relative to the non-inverting input, which is sometimes called the noise gain. And so even though the signal here is applied to the inverting input, you would calculate the bandwidth using the non-inverting gain equation. But really the numbers come out fairly close to each other. Ultimately, we take this gain and we take the gain bandwidth product and divide it by the gain to come up with the closed loop bandwidth.
Mm-hmm.
So the gain bandwidth product is 3 megahertz, but the gain of the device, the noise gain of the device, is 21, and we end up with the actual bandwidth is 143. So that's kind of an indication of, you would want to make sure that your signal frequency is less than 143. And what happens when we reach the bandwidth limitation for the amplifier is the gain starts to decrease. So the gain of this amplifier would be 20, minus 20, from the position of the input signal source. And when we reach this bandwidth limitation, basically the gain would start to decrease. It would go to less than 20,
Mm-hmm.
and it would eventually drop to basically 0. And so we can actually do a demo. Here we're going to look at circuit number 2. So
So I would like
turn
to
off.
just make summary. So
Sure.
basically it means you always divide this gain bandwidth product with the gain, with the how much you would like to amplify your signal. So it always reduces down. And if you really need like very high amplification, then you need really good op amp, because otherwise you would end up with very small bandwidth for your signal.
That's correct.
Okay, and
Yeah,
if you go
absolutely.
behind the bandwidth, then the signal or the frequencies about these frequencies are going to be amplified less and less and less and less. Okay.
Exactly. Okay, so I'm going to go ahead and turn off my power, and I'm going to disconnect my circuit. And we have the OPA 171 is what we want to use. And that's going to be in circuit number 2. By the way, this board here is kind of a training system that we have. And it's available on TI for people to kind of teach themselves op amps. So the video series that's associated with this is called TI Precision Labs. And you could buy this board and you could basically do the experiments and teach yourself analog. So I'm going to connect the output signal to the output pin here.
Mm-hmm. You
I'm
have
going
some
to
kind of
monitor.
special power supply, or what is it? This oscilloscope and power supply and everything
So
together, or?
it's a National Instruments virtual bench, and we use this for our training when we do this, because it's got everything all in one. It's got a voltmeter, it's got a signal generator, 2-channel oscilloscope. There's a 4-channel version, and it has a power supply. Even has some digital I/O. So it's actually pretty nice equipment for a college student, I would say. And
So two oscilloscopes.
y-
You
y-
connected two oscilloscopes.
yeah, I have 2-channel oscilloscope,
Okay.
and I have one channel of the oscilloscope connected to the input,
Mm-hmm.
and the other channel of the oscilloscope connected to the output. And then I'm going to connect
Oh
the
yeah,
function
that's what I was
generator.
missing.
Yeah, the function generator to the input, and now it should be ready to go.
Okay.
Um, so I'm going to go ahead and say import configuration, and we want to look at the bandwidth. Oh, wait, actually, so we wrote a special program for this one. And let me pull up the software for that. And so I'm going to run the simulate or the measurement from 10 kilohertz to megahertz, and I'm going to have 30 points per decade. And what I'll actually do is the instrument's going to measure the peak-to-peak signal level 10 times and average it. So first I'll turn on the supply.
Mm-hmm. So
And
this software is also controlling the device. Yeah.
yes, there's a USB connection between my computer and the virtual bench. And so I'm going to go ahead and hit start. And basically what's happening is we're applying an input signal shown in white. I think it's the white signal. And then the output signal is shown in red, being measured on the 2 channels of the scope.
Mm-hmm. So for
And
higher frequencies, the rate should. Ah, I can see it goes down.
yes, and then the range changed, so it looked like it jumped back up. But we're seeing the actual gain values being plotted on this Bode plot,
Mm-hmm.
which is what you call a frequency plot. And the gain here on the vertical axis is in decibels. The frequency is on the horizontal axis. And you could see that the bandwidth here is something like 100 kilohertz. It's when we go from this flat region of the curve to the region where it's rolling off, where the gain is decreasing.
Mm-hmm.
And so that's the entire measurement. And the way that you define bandwidth is by the 3 dB point, where the gain drops by 3 decibels.
Mm-hmm.
And so here you can see the gain is 26 decibels in the flat region or the DC region. And then if I go to 23, that should be about the bandwidth. So somewhere right about 150 kilohertz. So now if I go to simulation and I go to bandwidth, I can say analysis, AC transfer characteristic, and we run it for this OPA 171, same device, and you see basically the same kind of curve. And then if I look for the point where the signal goes to 23 decibels, I can just type it in and hit enter, and it jumps to that point. That's about 159 kilohertz. And here we measured 150 approximately. It's not perfect because I only have measured so many points, but you can see they're kind of close to each other. So you could simulate the bandwidth and you could measure it.
And you also calculated it, no?
Yes, we did.
And it
That's
was
right.
similar number,
Yeah,
143.
143.
Mm-hmm.
So yeah, and I actually like that approach of trying, when I'm designing a circuit, first, of course, I'll calculate it, then I'll simulate it, and hopefully the two numbers are fairly close to each other. And then when I measure it, if I don't get the matching number, then something's gone awry. And I spend time to try and figure out, is there some parasitic or some other factor that's, messing up my results.
Mm-hmm. Cool.
So, all right. So let's continue on. Slew rate. Slew rate is how fast the amplifier can move its output signal. And so oftentimes slew rate's measured with a square wave. And the reason is because when we apply that square wave, the output won't be able to jump instantly. Like a square wave has a very, very steep slope here. It's almost an instant change from 5 volts to minus 5 volts. And the slew rate will change or is specified in a number of volts per microsecond. So if we moved, for example, 0.8 volts as fast as we could, it would take 1 microsecond to move that 0.8 volts with this op amp. And slew rates can range from much less than 1 volt per microsecond to hundreds or thousands of volts per microsecond. So there's a wide range between, precision DC optimized devices and high speed type devices. So if I look at the slew rate simulation, I can say analysis. Transient is a time-based analysis. And before I run the transient analysis, let me just click on this signal source. And you can see that it's set up for a square wave. And then if I look at this, I can see the square wave's defined to have a 5 volt peak amplitude and a 10 kilohertz frequency. And so let's go ahead and do the transient analysis or time-based analysis. Now, 200 microseconds is selected because according to the frequency, that's going to give us a few cycles.
Mm-hmm.
And there it is. Well, you kind of saw it already. I pasted that figure in there. But if I put my cursor here, and I put my cursor here, basically at the 10 and 90%, approximately 10 and 90% point of the signal, I can use a calculator to say, well, the voltage change is about 8 volts,
Mm-hmm.
and the time change is about 11 microseconds.
Mm-hmm.
So 8 volts divided by 11 microseconds equals 0.72 volts per microsecond. And if we look back at our
0.8.
result
Mm-hmm.
here, 0.8, so it's pretty close. Okay, so we could do a demo for this one as well. So this is circuit number 5, OPA 277. Let me turn off the power and signal on, well, I'm going to close out this one, and I'm going to bring back the virtual bench.
So with this board, what you have, basically you can measure all these basic parameters of any op amp which you would like to use in your board.
Yes. And of course, it's true. The equipment itself is a limitation. It's all-in-one equipment, so it's not optimized for extreme accuracy. And then the circuits themselves are other limitations. Even with high-end equipment, oftentimes you have to use special configurations. So I'm going to go ahead and import the
but it's very nice to see
configuration.
that also simulation, datasheet, and measurement are similar.
Yes, absolutely.
Or at least we will see now again.
So let's see. We want the OPA 277 in circuit 5. So here's circuit 5, and I'm just going to put the OPA 277 in here. And there it is. We have our input signal, and our output signal and power supply, we're all good. We're all set. Let's go ahead and apply power. And then let's apply our input signal. And there it is. Now, I already set up a measurement to measure the rate of change. And so you could kind of see it over here in yellow and then also with these cursor indicators. And it says 743 volts per millisecond, which is basically 0.74 volts per microsecond. And so that corresponds quite well to the simulation and the calculation.
Unbelievable.
It is kind of neat. Even after doing this stuff a million times, I still am amazed. Okay, so slew rate. So now slew rate can actually impact sine waves. Frequently you look at it with a square wave, but what impact would slew rate have on a sine wave? Well, it's called sometimes full power bandwidth or maximum sinusoidal amplitude. There's different names for it. But long story short is you can use this equation right here to find out what's the maximum peak voltage that you can have at the output of the op amp without getting what's called slew-induced distortion or slew rate-induced distortion. And so you could use this graph right here and you would say for this circuit based on this slew rate, and the frequency of the applied signal, which is 50 kilohertz in this example, we could apply a sine wave of 2.5 volts peak, or 5 volts peak to peak. You could also use this graph, which is basically derived using this equation. So they're exactly the same. It's just two different ways of looking at the same thing. And if we go on the horizontal axis to 50 kilohertz and then meet the curve and go across, we get 5 volts peak to peak for our maximum output signal without distortion. So, so let's go ahead and look at what happens when we violate that spec. When we violate that spec, I can do a transient analysis. Well, before I do, let's just look at the input signal. So it's a sine wave input, and the amplitude is 10 volts, and the frequency is 50 kilohertz. And so if I run that 50 kilohertz signal into the op amp, we're going to violate the full power bandwidth or slew rate. And you see we have a nice sine wave going in, but what comes out is looking like a triangle wave because the output can't move fast enough to keep up with the input.
This is very interesting, actually. I would not say something like this happened.
It is, it's unusual. So
if you would like to keep nice wave, you need to lower the voltage. Higher the frequencies, you need to lower the voltage.
Right. So I'm loading my slew rate test. Wait, did I load the right one? Hold on. Import configuration from computer. Full power bandwidth is what I wanted to open. Okay, so I'll put on my power and I'll put on my signal generator, and you can see the input signal looks like a sine wave, but the output signal looks like a triangle wave. But if I reduce the frequency, let's reduce it to 10 kilohertz, and I'll just stop and start it again. Now you see that the output signal looks sinusoidal because we're not violating, or at least we're not violating it by much.
And if you go to 50 kilohertz and lower the voltage, I'm just curious.
Oh yeah, sure. 50 kilohertz. Boom. Okay, now let's lower the voltage. So let's make this, instead of 10 volts peak to peak, 1 volt. And stop and start it. Let me change the range here.
Yeah, I can see it now. Okay.
Okay. Yeah, so it looks sinusoidal. Right.
That's very nice. This is
Yeah,
very,
it's
I
kind of
think
interesting.
all this is very important when someone is, for example, building some systems which, I don't know, have to be very accurate, and maybe they have no idea that their signal may be damaged just because it goes through this op amp.
Yeah, yeah, absolutely. You know, if you did that to an audio signal, it wouldn't sound the same. It would sound completely different. Um, all right. So the last AC noise parameter that we're going to talk about is noise. Of course, there's other parameters such as distortion and so forth, but noise is my favorite topic. So let's take a look at that. Basically, uh, there's an intrinsic noise associated with the op amp. A lot of times we're talking about noise pickup from 60 hertz or from digital switching. That's not what we're talking about in this instance. This type of noise is intrinsic noise or noise generated by the op amp itself.
Mm-hmm.
And that's actually specified in the op amp. And that's probably the major difference between intrinsic and extrinsic noises. It's intrinsic is very predictable. You can calculate it, you could simulate it, and when you go to measure it, if it doesn't match the calculation and simulation, then something is not quite right. Like there's some extra factor that you haven't accounted for. It normally will match. You should be able to predict it. So we're going to use the same circuit we used for the offset test. But in this case, we're just going to look at the AC variation in the offset, which is the noise. And you can calculate the bias current by, and this is a very simplified calculation, but basically the way that noise is specified in the data sheet is a spectral density. So it's given in nanovolts per square root hertz. That spectral density is going to get multiplied by the noise bandwidth of the part, so that nanovolts times square root hertz is multiplied by the square root of frequency, and the square root hertz over square root hertz will cancel, and we just end up with the RMS noise in volts. So in order to do a noise calculation, you'll normally calculate the noise or get the noise from the data sheet. And there's also going to be noise from the resistors. The resistors have a thermal noise. So the noise of the resistor can be calculated with this analog engineer's calculator, which is something you could download from TI at no cost. And there's a variety of different tools here, but the one that we care about now is the thermal noise tool. And if I put in the equivalent resistance, and what was that? It's about 1 kilo ohm, 0.99 kilo ohms. If I put in 0.99 kilo ohms, it tells us the noise density is 4 nanovolts per square root hertz. And that's where this number comes from. It comes from the calculator. And then the op amp data sheet provides the number for the op amp. And to combine those two, you add them as the square root sum of the squares. We call that RMS summation, or adding the two numbers that are uncorrelated noises. And when we add this 8.8 and 4 using that method, we get the total noise density is 9.7 nanovolts per root hertz. Then we can multiply that by the gain to find the output noise density, and then we can multiply that by the square root of the noise bandwidth to get the actual RMS noise at the output. And then the peak to peak is normally about 6 times the RMS. Now, this noise is, I mean, it's a subject that I've spent most of my career studying, so I can only kind of touch on it very briefly here.
I
But
think we
this
did
is
one video before about noise, which is a little bit more
yeah,
detailed. So if someone would like to
yes,
know more, they can watch the video what we did before. And sorry
exactly.
for interrupting. So I'm curious because Before, the noise was kind of dependent from the frequency, and suddenly 3.6 millivolts RMS. I don't understand this.
Well, it's actually a good question. So there is noise across all frequency for resistors and for the op amp. Let me pull up the data sheet for the OPA 188 really quick. And I'll just say, let's find the noise curve. Uh-oh, there's too many of them. I'll just have to scroll to it. Okay, so there's the, here we go. This is the key point. So this is the noise versus frequency. Notice that it has the noise density in nanovolts per square root hertz. It's about 10 nanovolts across all frequency. So there's basically noise at all frequencies, and depending on what the bandwidth is, we're integrating this curve. And so if we have a wide bandwidth, we get a lot of this curve. If we have a narrow bandwidth, we get less of this curve. And that is why the noise will increase for wider bandwidth. Basically, the way that we convert this noise density, which is nanovolts per square root hertz, to a voltage is by multiplying the nanovolts per square root hertz by the square root of hertz, or really the square root of the bandwidth. And then from a dimensional analysis perspective, the units will cancel. Square root hertz divided by square root hertz cancels. But the key point, though, is that we're integrating under this curve, and that's how we're finding the actual total noise. And so the total noise is going to be about 3.6 millivolts RMS, which on a peak-to-peak scale should be about 22 millivolts. So it should show up on the scope quite well. Let's go ahead and put in these circuits. Let me turn off the power and signal on this. We did already, good. All right, so we're really building the same circuit we did before.
It's clearly not your first time using this board.
Yeah, I've traveled around quite a bit with this one, and yeah. So
how many op amps you damaged when you plug them in the wrong way?
We've damaged many. We have definitely put some in backwards. So I'm trying to remember which one should be which. Okay, we'll put them like that. So again, we have no input signal here. We're just grounding the inputs. And so I'm taking off the function generator. And we're going to look at channel 1 is the OPA 211, and the channel 2 is the OPA 188. So we'll look at the noise of those two separate.
So now I guess the one which was good for DC will be worse for AC and the other way around?
Well,
I'm curious.
It's not quite exactly true. You actually, the OPA 211, the one that was not as good from a DC perspective, is the lowest, one of the lowest noise devices we have. So you would expect it would have really good noise performance, but in reality, its current noise which is really the bias current noise of the device, is not as good as the OPA 188, the DC optimized device. So actually, in this case, I think I've got them backwards. That's what I was trying to figure out. So I'm just going to switch the channels so that
Okay.
the scaling is a little bit better. So we are measuring on channel 1 the OPA 211, and channel 2 we're measuring the OPA 188. Okay, so you could see I'm showing the RMS level of the noise, and we're measuring about 5 millivolts RMS, and for the one device, and 11 millivolts for the other device. And so let's do the simulations for noise. So the OPA 188, if I say analysis, noise analysis, and we're going to show the total noise, the integrated noise, I end up with about 3.5 millivolts RMS. And then if I look at the OPA 211 noise analysis, and we get about 10.7. So
3.5 and 10.7.
3.5 and 10.7. And so we go back here and we get about 5 and 11. So is it perfect? No, but the measurement instrument does have some limits to it. And then there's always going to be some process variation.
But it's pretty close.
You definitely, yeah, it's pretty close. Now, here's the really cool thing about noise. I can filter noise. So if I click this switch, and if I click this switch, we will basically filter this first stage. And so if I do the same analysis, the noise will drop to 1.9 for the OPA 188, and then noise for the other device, it's less than, or it's about 0.5 millivolts or 500 microvolts.
But I guess you
So
limit bandwidth or something with
yeah. Basically, this capacitor is in parallel with this resistor, the feedback resistor. So if you think of a capacitor at high frequency, it acts like a short. And so if we short out that resistor, the gain of this circuit, which is RF divided by R1, or in this case R8
will
divided
change
by R12,
for higher frequencies.
Yeah, it's going to drop. It's going to basically go to 0 at some point. What happens if I do that? Yeah, you're right. You're actually right. I shouldn't have said 0, but
0 resistor will be 1. 0, but the gain will be 1.
Yes, you are absolutely correct. So if I put this filter in, I put jumpered the filter capacitor, and you can see the noise basically drops to almost 0 or very low, beyond the measurement of the instrument capability of the instrument. And so there it is. We've greatly improved our noise by limiting the bandwidth. Of course, at some point you can't limit, you're also limiting your signal bandwidth. So if you need a wide signal bandwidth, then you will not be able to do this, but you can basically always limit your bandwidth to what your signal will tolerate. So if you need, let's say 20 hertz to 20 kilohertz, well, then you could limit your bandwidth to, maybe you wouldn't want to limit it to 20 kilohertz, maybe you'd limit it to 200 kilohertz to give yourself a little margin, but you wouldn't need megahertz of bandwidth, and that would just be extra noise that you would get by leaving the circuit unfiltered. So the moral of the story is, to reduce noise, you filter to the greatest extent possible that your input signal will allow.
Because noise is generated for every single frequency, as we see in the graph. And if we can just cut off the noise from the higher frequencies, then we can drop the total noise down.
Right?
Okay.
Exactly.
I understood.
Excellent. Okay. And I mean, I mentioned distortion is another important one, but I'm not really showing that here. What we're going to do now is move on to the functional specifications.
Okay.
And by functional specs, I mean things that if you violate them, the amplifier is really not going to function correctly at all. And so the input range and output range and stability are things that if you violate these, you're going to not damage the device, but it's not going to really act like an op amp. First we'll look at the input and output range of the device. And basically the input and output range are always relative to the power supply. You can never get out more than the power supply range. So in this case, the positive supply is 10 volts and the negative supply is 0. You could connect this to -10, and different amplifiers will allow for different power supply ranges. So the input signal also is going to be related to the power supply. There's what's called a common mode signal, and that's really the signal that's applied to the non-inverting input. That's the common mode signal. Because remember, there's a virtual short between these two inputs. So if you put 1 volt on the non-inverting input, then the inverting input will be pretty close to 1 volt, and the common mode voltage is basically 1 volt. And so there's a common mode range relative to the power supply, and there's an output range relative to the power supplies. Now, the common mode one is a little bit more difficult to understand because it really relates to the op amp configuration. So, for example, an inverting configuration, usually you don't need to worry about the common mode range of the op amp. And the reason is the common mode, as I said, is the voltage on the non-inverting input, which is also the voltage on the inverting input. It doesn't matter what the input signal is in this inverting configuration, the common mode is always going to be 0 in this example. So there is no common mode limitation due to the input signal here because the common mode's fixed by that. Now, in a non-inverting configuration that's in low gain, whatever's applied to the non-inverting input is going to be the common mode signal. So if Vin is 1 volt, the common mode voltage is 1 volt. And in this case, the common mode is limited from -0.1 to 0.8 of a volt. And this is given in the data sheet of the device. It tells you what the common mode range is. And so if we apply a 0 volt to 10 volt input signal, when we get to 8 volts, we violate that common mode range and it doesn't function anymore. We just get nothing out. We eclipse basically. So you do have to pay attention in a non-inverting configuration to the common mode. But if the gain is really high, it doesn't usually matter. And the reason is whatever the output signal is divided by the gain on the input. So if the gain is 10, as is shown here, 90K divided by 10K plus 1, if the gain is 10, then the input signal,
will
for
never
a
be
10
8
volt,
volts.
right. It's going to be between 0 and 1 volt, basically, to get 0 to 10 out. And so you're never going to reach that point. So the main case where you worry about this common mode is low gain non-inverting configurations. So here we go. Here's our circuit. We're going to look at the OPA 140. Let's go ahead and look at the simulation first. So if I
You have simulation for everything.
Yeah. Yes. If I say, well, let's look at the input signal. The input signal is a triangle wave. And I just use a triangle wave because it's easy to see the common mode limit. And its amplitude is 4.5 volts a peak on a 5 volt supply, 50 kilohertz. And if I run the analysis, again, we're looking at a time-based analysis or transient. And the input signal is a nice triangle. It's a buffer, so the output should be the same as the input, but it clips, basically, due to the common mode limitation. And so let's get the OPA 140 going. So I'm going to turn off the virtual bench and remove these circuits. And this is circuit number 5. So here we need an input signal again. So I'll connect my function generator to the input, and I'm going to connect channel 1 to the input as well. And channel 2 will show the output. So we need our op amp, which is OPA 140. Here it is, OPA 140. And there it is. So it's all connected. And I can say file, import configuration, and we want common mode, input common mode swing, and apply the power, apply the input frequency. And you can see, here's an interesting thing. So the real device doesn't clip like the simulation does, but you can see that it's very distorted. It's really not functioning correctly. So the model in this case is showing a worse case than the reality, but bottom line is the part's really not functioning properly as a normal op amp would in this region where we're violating the common mode. So sometimes people expect that the amplifier will always fail or be as bad as the simulations, but the real device could actually be better than the specs. It's not always going to be equal to the worst case spec, but it could be better than the worst case spec. So that's what we're seeing here. Okay, so what about output range? That's the kind of very similar type response here. And I didn't show this so much with the input range, but the calculation is essentially the same. The way that input and output range are specified is it gives you the minimum output range or minimum input range and the maximum output range. And it says relative to the power supply, we can go above the negative supply by 0.5 volts and below the positive supply by 1.2 volts.
If we use the RL 10K or 2K, okay.
That's right. Yeah, actually, good point. Thank you for mentioning that. So the output swing, since the output current is being driven from the output of the amplifier, it's affected by the load impedance. Basically, if a load impedance is really small, we're going to drive a lot of current, and there's going to be internal voltage drops that prevent us from reaching this. So let's go ahead and look at the simulation. So we're going to output swing, and I say transient analysis. And now you can see, you could definitely see we're violating the positive swing. And we're even violating, you can see a little bit, the negative swing. And notice that we've got a plus or minus 2.5 volt power supply, and the input is plus or minus 120 millivolts. So you know that is not probably going to violate any input swing limit. But it's in a gain of negative 20. So the output is much larger than this input signal. And the output swing wants to go to 20 times 120, but it clips.
So what is the output load here? We don't have any.
The output load, that's a good question. So the the voltage on this point right here, the inverting input, is 0 volts due to the virtual short. And so basically there's a 0 volts here. And so the output is at this point, and thus the load is this 120
20K.
kilo ohm. Yeah, so actually you don't, oftentimes people say, well, there's no load, it's infinite, but that's really not the case because the feedback network itself will constitute a load. So, well, let me connect the circuit first. This is circuit number 2, and we're using the OPA 277. And the input signal and output signal connections are the same as the previous case. And we've got our everything connected. So let's go ahead and load the configuration. And we want output swing. I'm going to apply the power, apply the input signal, and you could see that it's distorting on the negative and also on the positive, very similar to what the simulation indicated.
This is also important because maybe people may think like I can go up to the power, but no, you can't go up to power.
Yeah, very true. In fact, there are devices, special devices called rail-to-rail devices that the input swing is basically from the negative supply to the positive supply. The output swing will get really close to the positive supply. So the output isn't really true all the way to the supply, but on a rail-to-rail device, it can be within millivolts. And of course, it depends on the load resistance. But
so in real applications, maybe your power supply should be kind of much higher than what you really need, or what you would, what kind of output you need. That's what I mean, an input.
Yes.
So if you are, for example, if you are working with 5 volts, maybe you would like to use 10 volt power supplies.
It can be true. For a rail-to-rail device, you could swing pretty close to the 5 volts. One thing you do have to be a little careful of, let's say that this op amp was driving an A to D converter, and the A to D converter has an absolute maximum input range of 5 volts, meaning if you exceed 5 volts, then you could damage the device. If we put a 10 volt supply on the op amp, the op amp might be able to drive the 10 volts and could potentially damage the next stage. So one thing about these examples is I intentionally picked devices that don't have great swing to the rail to exaggerate the problem a little bit. There's some that are better, than this, from an output swing perspective. So, yeah. Okay. Wait, did I? Yeah, I did show this. All right. So the last functional spec is stability. And stability relates to the ability of an op amp to drive a capacitive load. You might think that an op amp could drive resistors, capacitors, inductors. It just doesn't matter. But the fact is that what'll happen when you try and drive a capacitor is the op amp can have a lot of overshoot and ringing, or even can oscillate continuously. So you might have a DC signal in and get an AC signal out, and that's not a good situation. So you really want to be careful about driving capacitive loads. We have a whole series of videos on how to stabilize amplifiers. Sometimes you do have to drive a capacitive load or an inductive load. So how do you do that? Well, there's a lot of different ways that you can make an amplifier drive that capacitor, but the very simplest is to simply put a resistor between the op amp and the capacitor, and selecting the values, it requires the use of some math and so forth and simulations, but we're not going to cover the details of that today. But basically, we'll see that if we connect this capacitor directly to the output of the amplifier by shorting this resistor out, that will get a lot of overshoot and ringing or oscillations. And if we then put this resistor into the circuit, we'll see that we get a good result.
Okay,
We
I'm
don't get
curious.
oscillations anymore.
Again, something what I
So
would not expect.
yeah, so let's take a look at the stability. First, we'll short out that resistor, and I'll show that the input signal is a small step, a 10 millivolt input square wave. And to test stability, you really want to use a small signal because we don't want this amplifier to go into slew rate operation. We want it to be a small signal. And we're going to use 10 kilohertz. And let's see what happens when we apply this transient signal. So you'll see it doesn't look really horrible, but instead of having this nice square wave on the output, we have overshoot and ringing, and depending on how large that capacitor is, this could actually just become an oscillator. So the different capacitors will cause different amounts of overshoot and ringing, and it might look like it kind of settles out here. But if you were to zoom in on this, you might see very tiny oscillations that are unacceptable for good accuracy.
Mm-hmm.
So if I then open this switch and I do the same analysis, and so now we have the isolation resistor, you can see that the load signal has this capacitive exponential rise and fall time, but the output of the op amp is really what you look at when you're checking stability. It has a tiny bit of overshoot, but then settles out very quickly. And this is a very common problem that we deal with, where people want to filter their op amp output, and they just connect the capacitor directly to the amplifier,
Mm-hmm. I
and you get
understand.
this stability problem.
Mm-hmm.
Or even sometimes it's, people know that they can't have a big capacitor on the output of the amplifier, but they're driving a cable, and cables can have a lot of capacitance, and that can cause an op amp to oscillate as well. So let's take a look at this circuit. This is circuit number 5, OPA 277. And so I'm putting my jumpers back in.
Your power supply is on.
Oh, thank you. I will turn all that off.
I just see the blue LED, or what is it? I don't know.
You're right. Thank you.
I don't want you to damage another op amp.
So first, I'm going to connect the capacitive load without the isolation resistor.
Mm-hmm.
So the isolation resistor is shorted out. And I'm going to apply the signal on the input, but I'm going to look at the output signal on the output pin of the op amp, but also, pardon me, I'm looking at it here and here.
Mm-hmm.
At these 2 points.
Mm-hmm.
The square wave we know is a square wave. We don't need to really look at that.
Mm-hmm.
But the point at which you really should examine the op amp for stability is right on the output
Mm-hmm.
of the op amp and not across the load here.
Because I guess that's the feedback which goes back, and then that's what can make the problem.
Yes. And there is no resistor here. And in fact, in this case, with this shorted, they're actually the same. Yeah. But when this resistor is in place, the RC operation can filter out any oscillations, whereas the amplifier is still not functioning correctly. So you want to look at the output of the op amp. So we want to import the stability, and we'll apply power, and there it is. So they're the same signal in this case, but you can see that we get a large overshoot and ringing, and you can even see, if you look closely, Yeah, it does. So now all I have to do is,
At the jumper. Oh, remove the jumper.
right, exactly. So now that's gone, and let's see what the signal now looks like.
Mm-hmm.
So we get a tiny bit of overshoot. The output across the load has this exponential rise. So you could even see, to my earlier point, like there is a little overshoot, not much. It's acceptable. But if you were just looking across the load, you'd see this and you wouldn't think there's any overshoot.
Mm-hmm.
Now, I should say that this analog engineer's calculator also has stability tools. So we can look at versus percent of overshoot. What's the phase margin? So let's say there's 20% of overshoot. The phase margin is 48 degrees. And again, stability is a deep topic, but basically a phase margin of 45 degrees or better would be good. 45 degrees or higher. So that would be stable with 20% of overshoot. But if the overshoot were 30 degrees, then we would have less than 45 degrees, and it would be what we consider to be marginally stable or unstable.
Mm-hmm.
And the larger the overshoot
So
gets, the
if
worse
phase is
things are.
too low, then it may start oscillate, or
Mm-hmm. Yeah, it could be oscillate continuous if it were, in the 10% range or zero, of course, it would oscillate. Even like the Bode plot we saw earlier, when a circuit's unstable, it gets AC peaking. So, for example, if I have AC peaking of 4 decibels, it starts out at 0 and jumps up to 4, let's say. That means the phase margin is 36.8 or almost 37 degrees. So that would be an unstable situation as well. So you could look at the Bode plot, the AC response, or you could look at a small signal step and the amount of overshoot and ringing you get to see whether a circuit's stable or not.
mm-hmm. Yeah, can you go back to calculator? I'm just curious, what is inside of the
Sure.
PCB?
Oh, yeah. So this is one of my favorite tools. It's
Oh,
a
I didn't know
transmission
you have
line
something like
simulator.
this.
And you can see that you can like change the length and the width and so on and so forth. And it will calculate the characteristic impedance. And it's basically looking at the reflections of this trace. And you can adjust the various different parameters via inductance and capacitance, parallel traces, microstrip, um, PC board, parallel plate capacitance, and the
Okay.
trace resistance. My favorite one is this one. A lot of these tools are found elsewhere as well. I use the via inductance calculator a good amount, but they're fairly standard. There's tools for A to D converters, tools for amplifiers, various different tools. Passive component ones. Uh, these seem kind of basic, but like parallel.
It
What
helps.
standard value? How do you get an unusual value? Let's say 112 ohms. Maybe it's not a standard value. You could get 100 ohms and a 12 ohm resistor in series, and you'll have 0% error. So the standard value is the key here. But yeah,
Cool. So now we will be doing demo with Zach.
yes.
We are going to have a look on practical example where op amps are used, and Zach is going to explain what is on this board and what it actually does.
Okay, so this is an evaluation module for a device called the OPA 928, and this device has an input bias current typical of about 1 femtoamp. So femto, that's times 10 to the negative 15, and 1 femtoamp is essentially 6,000 electrons per second. So being able to resolve currents that low down to 1 femtoamp, it's a very difficult design to achieve. There's a lot of errors you have to account for. So I developed this specialized board that you can see here that has a layout that's able to resolve those types of current levels.
So basically it's special because it can measure very low currents.
That's right. I'm able to measure all the way down to 1 femtoamp. And you'll see we have an RF shield on the top of the board here. We also have a couple of shields on the bottom, and those are going to completely enclose all of our high impedance nodes. When you're interacting with a high impedance sensor, you have very small currents. It's very sensitive to any kind of capacitive coupling, electromagnetic interference from the outside world. And I'll show you an example of that later. What happens if you don't properly shield these, then your signal goes all over the place.
Okay. So what do you have on your slides? Let's talk about this a little bit. I see there is layout on page number 31. Can we have a look on layout?
Yes. So one of the ways that we can achieve the femtoamp input bias current is by making sure that there's no other current leaking into that input pin. So you may think that your PCB is a perfect insulator and that there's no other parallel paths, but of course in real applications, your PCB layout itself is a component. And if you have something like a power supply or a voltage on the board, then that presents essentially as a large resistance, and then you're going to have current flowing from your power supply into your input pin, and that can be, you know, femtoamps or even picoamps of current. So what we do here is we have a guard structure that goes all the way into the board layers by using vias and these copper pores.
You can use mouse. You can use mouse to show the area. Yeah.
Yeah, so that's this area here on the surface layer.
Mm-hmm.
And you'll notice that this is connected to this pin, which is actually an internal guard buffer. So this monitors the voltage at the input, and it's a voltage follower so that this copper is the same potential as your input. And if they're both the same potential, then there's no current flowing in between them.
Mm-hmm.
So that's how you protect it from any other leakage paths on the board or in the outside world or even inside the board through other vias or other layers.
Okay. Next, what do we need to know before we start some measurements? Like maybe a little bit more about the probe or what we are using?
Yeah, so today we're going to be looking at a pH sensor in order to measure the pH of a couple of materials here. And what is a pH sensor? Well, the most common form is this combination glass electrode that you see at the bottom of the screen. This is actually the exact one that we're using today. It's one of the Hamilton probes, EasyFirm Plus. And these can have an impedance up to 10 gigaohm glass impedance. So any kind of input bias current going across that impedance is going to generate a very, very large offset voltage. And that's what we saw in this in the previous slide, where when you're interacting with them, you need to make sure that bias current is very, very low to keep the errors down. And essentially, these work by generating very small bias voltage based on the ion activity in the solution. Mm-hmm. So this is always referenced at the inside of the glass to a pH of 0 or a pH of 7, excuse me, which is the perfectly neutral. It's the center of our pH scale here. And then when you have a solution on the outside of the glass, that generates a voltage based on that ion activity. And the difference is determining what that pH is. And that's dependent on the Nernst equation here. And it gets very complicated. There's a lot of chemistry and physics into this technology, but all we need to know is that, at room temperature, the sensor is going to generate about 59 millivolts per pH, and could be positive or negative, and it's centered around 0 millivolts. So if it's a neutral solution, we'll read about 0 millivolts. And then if it's an acid, we'll get a positive voltage, and if it's a base, we'll get a negative voltage.
Okay, so let's have a look again on the schematic. I just would like to see what is the connection. So it's like super simple, the schematic?
Very simple. We're just going to be buffering. So we have our high impedance amplifier here, and we're going to just monitor that voltage at the probe and buffer it to read it on the output. And why do we have to do this? You say, why can't we, just connect a digital multimeter or something like that to measure it directly? Well, that's because of this input bias current. So you can see at the bottom here, if we selected the wrong amplifier, this is actually a bipolar amplifier, and the input bias current is about 50 picoamps. So our pH probe model here, we're assuming that it has an impedance of about 2 gigaohm, and it can be even higher than this. And we're assuming that it's measuring a pH of 7, so it wants to output 0 millivolts. So in this case, the pH probe is actually 0 millivolts, but because of this bias current, we're going to read 100 millivolts at the output. And that's going to make us think, instead of a pH of 7, this is actually a negative 100 millivolts. So we're going to think that we have a pH of 9. And that's a very significant error.
Mm-hmm.
So for our high impedance amplifier at the top here, we have the model shows 2 femtoamps of input bias current, and you'll see our output is showing almost 0 volts. This is some nanovolts or microvolts you might expect. So I can go ahead and show you the measurements that we can take.
Yeah.
I have it set up here in this configuration. This one here is orange juice. So it's going to be acidic. We'll probably expect it to be somewhere around a pH of 4. And then this pink solution here is it's milk of magnesia. It's kind of a medicine people take for upset stomach, and that has a very high pH. It's very basic. So we're going to expect to read something around maybe 10 for this one. So right now I have the probe back here, and this is in a buffer solution that is perfectly neutral. Essentially, it has a pH of 7, and if you can see the output of our probe here, the digital multimeter, the output of our electrometer solution, we're reading about 2 millivolts. So there's always going to be some offset to these pH probe sensors themselves. It could be as high as 20 millivolts or even 30 millivolts. This one, the pH probe, is showing 2 millivolts of offset, so that's still quite a good probe, all things considered.
What is red and what is yellow?
This one here?
Or on the screen?
Oh, I'm sorry. We're really just looking at this digital multimeter here at the bottom.
Okay.
This is we're just reading the DC voltage. I wish I could make this bigger, but I don't think I can.
No, it's fine. It's fine. I was just confused, like. And now you are using the good one or the bad one, the amplifier?
Oh, so this one, we just have our OPA 928 EVM. So this is the only one we have set up. The other, that schematic was just an example of showing what you can expect to see if you actually set it up. But I actually don't want to pull too much current out of this probe because they can be very sensitive. And if you actually pull too much current out of them, you can even damage them. So I haven't heard one of these probes yet. So in the interest of making sure that that's the case, we're just going to show the optimal solution here.
And why there are 4 connectors on the board?
4 connectors on the board. So this evaluation module, it's actually has 2 different circuits. We're using the one on the top here, and this is our high impedance buffer amplifier. And the one on the bottom is actually set up for a transimpedance, and that's going to be to measure very, very low femtoamp currents. This one's disconnected. We're just going to use the one at the top to amplify our high impedance signal.
Okay.
So let's take a look. If I take it out of the buffer solution here and I place it into our acid, now we can see we're reading about 160 millivolts, and these things, once again, they're very high impedance, so they tend to have a long settling time. It could be 30 seconds or even longer. But it looks like it wants to settle around somewhere between 170 and 180 millivolts. So if we remember our Nernst equation, 1 pH is going to be about 59 millivolts. So centered around 7. So if we're reading 160 millivolts, that's about a pH of 3, because it would be.
So it will be like 10
4.
Do we need to do 7 plus 3 or?
It would be so for an acidic, it's going to be
minus.
positive. So yeah, so it would be about 3. So 7 minus 3, a pH of about 4.
Okay. Okay. Good.
So now we can go ahead and move on, and I'll just try to rinse it off in this deionized water here. And one thing to note is this is deionized water, so it should have a pH of 7, just about neutral, but we're still reading as if it's an acid, and that's because this water is deionized. So this probe actually measures the ionization activity, and there's very little ionization activity in here, so that can give you a false reading. But our base over here is going to have a lot of ionization activity, so we're going to be able to see the voltage now changes. So it's about the opposite of what you expect. The basic solutions is a higher pH has a negative voltage within its equation. And this one about 160 millivolts, so a little bit less than 3 in this case. So we're reading about maybe 9.5 pH.
Okay.
For our milk of magnesium.
Cool. And this is the reason why we need to know how to actually design op-amp circuits properly, because, for example, for this specific application, if it's not done properly, then it's not going to work.
That's right. And I'll give you one good example of that. So I don't know if you can see in the camera, but with this demo, we have a little bit of exposed wiring where we were connecting it together. And of course, we had to place it in this tin can here, which is connected to the analog ground of our circuit. And that's to shield those cables from any kind of interference. So this is a very good shield connected to ground. But you'll see what happens if I actually remove the ground connection and I leave this tin can floating. So we have 2 ground connections here. I'll just remove both of them. And now all of a sudden, if I wave my hand around the assembly, we can see our voltage is changing very drastically. If I wiggle these cables here, the voltage is going all over the place simply because of the capacitive coupling. Even, you know, just my body has a charge to it. It has a very small magnetic field. And bringing this into close proximity, it's going to couple into the signal because it's such a high impedance.
Wow.
So,
I think it was over 230, or what was there? Like, yeah.
Yeah. And then as I back away, and if I hold really, really still, it'll settle back down. And then if I go close again, and I start waving my hand around the assembly, the voltage just goes. And it's just because of it's such a high impedance that any type of charge, moving charge in the proximity will couple directly into the circuit and give you some pretty significant errors.
Wow. Thank you so much, Zach, for this demonstration.
Absolutely. Thank you, Robert.
Thank you very much, Arthur. This was super useful. I learned so much. And as I said before, I really wish they would explain, they would use this way to explain op-amps at university, because this was like super easy to understand. So thank you.
Thank you. I really appreciate the visit, and it's really nice. I hope this is useful to everybody. Have a great day.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEval online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.